which is used for like some hardware-related stuff like power management software. You can consider that ring -2. And then if you look at the slides for Black Hat USA from 2009, the Invisible Things Lab had something on the AMT environment, which was interesting, and I guess you could consider that a ring -3 rootkit. So this is kind of a trend, and that is that the vendors try to create these fortified regions of execution where they say, okay, we want to protect ourselves a little bit better by going outside of this 2-ring model and getting to a higher or lower ring, I guess you'd say that. Getting to a lower ring where we'll be a little more protected from malware. So it's not a bad idea, but what happens when the malware finds its way into those lower rings and subverts that? So the downside of going into these, like, the rogue hypervisor or SMM mode or the AMT environment is that it's really hardware dependent. And as an attacker, if you don't have physical access and you don't have anyone on the inside, you can ping for information about the information you're trying to get at, and you don't necessarily know what type of hardware you're really targeting. You might start off doing a network-based attack where you follow that whole like hacking exposed methodology where you footprint and then you do a host enumeration and then you start scanning for services, yada, yada, yada. And what you finally end up with is maybe a network scan of all the services running on a machine. So all you start off with is that list of services. You don't know necessarily what hardware you're running on. And so you can't kind of prepare in advance to have a rootkit which is going to target this firmware on this motherboard, and you don't have any of that information. So that's kind of the downside of these bleeding edge stuff. It's impressive work, no doubt about it, but it's not always realistic to assume that's going to be there for you to leverage. So we have to make concessions, right? We want to hide, and we want to be able to conceal our rootkit and anything else we might be doing. At the same time, we want to remain hardware agnostic as much as possible. Obviously, my talk, I'm targeting Intel. So when I say that hardware agnostic, I mean a specific external peripheral chipset or something. Maybe a video card or something, or a BIOS chipset. So I wanted to kind of avoid having to anchor my code to that kind of hardware. So we have to reach a middle path, as they say in Zen. We have to find a compromise. And so one potential middle path is Shellcode. You heard me. So Shellcode offers a little bit of autonomy because it doesn't rely on the system loader. It doesn't need address resolution. You just basically plop it into memory, and you don't have to do anything else. And because of that, all those bookkeeping data structures you would normally be updating when you load a module, whether it's a driver or a DLL or an executable or whatever, none of that happens. And so you have there's less. You're leaving less of a footprint on the system. At the same time, you have some portability because you're just basically using the core Intel instruction set. You're not necessarily relying on a specific BIOS chip. So we have this middle ground, right? Now, obviously, anyone who's worked with Shellcode knows that it can be complicated to. After a certain point, the whole reason of higher level languages was the complexity of dealing with low level machine instructions. Even in assembly, it's a pain in the butt. After anything more than 1,000 lines of code, it just becomes, there are conventions you can adopt to kind of ease the pain, but it can still be unpleasant. So you'd think that there'd be some way around this. Maybe we could write shellcode in C. Wouldn't that be nice? And just, and so we could deal with it in a high level language. And there's actually been work that's been done on that. Back at the Black Hat Europe 2009, there was a pretty cool thing that this guy built. And it's like it's a shellcode, and it will build shellcode for you. So there are different types of shellcode. Obviously, I said the Intel has the 2-ring model. You have a user mode and kernel mode, and you can write shellcode for either or. I prefer kernel mode shellcode because the kernel's a little more opaque. There's a little more entropy, I think, in the kernel. Also, by executing in the kernel, you're on equal footing with security software for the most part. Most security software, if it does, there haven't been that many products that will go into hypervisor mode and be a watchdog. Most of the stuff will just maybe have a kernel mode driver presence that they'll stick in the kernel. And so if you just stuck and you just plopped your stuff in user mode, there really wouldn't be much of a way for you to fight back or preempt. But in kernel mode, it's toe to toe, and I think you have a bit of an advantage over security software in that sense. So I liked it because it basically offers me a little better concealment and some more powerful features. So we looked at concealment, and we ended up having to make a compromise and going with Shellcode. And so now let's tackle the other design goal, which is surviving reboot. Some people would say, why do you even have to worry about surviving a reboot? I mean, the enterprise systems like IBM's Z series, their flagship mainframe product, which is really the bread and butter of IBM's enterprise, tradition. No one ever got fired for going with IBM, and this is what distinguishes them. Basically, I think they have these mainframes that are built, and all around it's all about being up and available and stable. And so it's like, well, these systems don't go down. Why do you even have to worry about a system restart? Well, as it turns out, this isn't always the case. There are high-end deployments where they actually do reboot their machines, like the Chicago Stock Exchange. The exchanges are open for so many hours every day, and after the markets close, they have the luxury of rebooting all their machines. Or there'll be other installations where what they'll do is they'll institute rolling restarts, so that they don't turn all the machines off, they turn a subset off, and then it just rolls through the deployment. So one way so there actually is an issue. You do kind of have to worry about a system reboot. You can't always depend upon the server being up. So why not plan for the worst and have a contingency in place? And one way to kind of get ideas is to look at the commercial vendors and the solutions that they've used to implement self-healing software or fault-tolerant software. There's a company called Absolute, which sells a product called CompuTrace to that end. It's an inventory tracking. Officially speaking, it's inventory tracking. So if you lose your laptop, it will help you get it back. And so this product consists of two different components. There's an application agent, which is that RPC net.exe. And it runs as a service. And like I said, it kind of blends in with the other services. And what it does, at least the version that we use at San Francisco State, what it does is you can, if you're watching it through Procmon, the sysinternals tool, you can see that it will launch a web browser, and that web browser will do a post over HTTPS to the mothership, and that post will be sending information, ostensibly inventory and software management information to Absolute every so often. And then there's the other part of it, which is a persistence module. The persistence module is actually the stealthy component. They usually install it on the disk partition gap. And there's a bunch of laptop models and stuff nowadays that actually have firmware level support, which is really kind of a really work intensive process, because they have connections with OEMs. So they actually can get access to the specifications they need to do this. As a black hat, you're not going to have any vendor cooperation on anything. So it's a little more problematic in terms of embedding stuff in the BIOS. It's a lot more work. Back at the Black Hat 2009 USA, and when the Invisible Things Lab did the AMT environment, I think I overheard Joanna Rutkowska say that the work that they did on that represented like 6 months of reversing effort. And so I'm thinking, Absolute doesn't have to worry about that, because they go to the vendor, they get the spec, they get any information they need, they don't have to do any reversing. And so all that energy that they would have spent on reversing can be devoted strictly to development. And so that's, in a sense, that's kind of a distinguishing feature, I think, between commercial software and